Okay, so good morning, everybody. This is now lecture 13 of the Logika course. And today we're finally getting to the material we've been building up to for essentially the whole course. And today's lecture is going to be on Gödel's incompleteness theorem. Actually, Gödel has two incompleteness theorems, and so today we're going to cover the first one. So today's lecture is Gödel's first incompleteness theorem. So to set it in context, last week we had axiomatic theories of arithmetic. Of which the most important was piano arithmetic. But we also saw that we got various fragments of piano arithmetic, so we could restrict the induction axiom to restricted class of formulas, so such as sigma 1 formulas. That gives us the restricted theory I sigma 1, or even further to delta 0 formulas, so that gives us an even more restrictive theory I delta 0, or even further, instead of having any induction at all, we could simply add one more axiom that we need in the absence of induction in order to do anything, and just have this theory with 7 axioms, Robinson's theory Q. And we already saw last week that piano arithmetic, although it looks like it's all the axioms we could think of for the natural numbers, that it's incomplete. So we've already seen an incompleteness theorem. And we saw that the purpose of Q was that we were able to prove that any reasonable extension of Q that we can axiomatize will remain incomplete. So even if we try to extend piano arithmetic with some new axioms, we're still going to get an incompleteness phenomenon. So let's put a ring around piano arithmetic, because it's the sort of the most important one. So we saw what those theories are last week, and we did some basic properties, reasoning in Q. In the exercise classes, you did some other basic properties, either proving things by induction, I think always in I delta 0, or showing that Q can't prove even some very, very basic things, statements about the natural numbers. But piano arithmetic, as I say, it's kind of got all the axioms that one would naturally think of for the natural numbers, and it's the canonical axiomatic theory of arithmetic. So we saw the axiomatic theories of arithmetic, and we already saw the incompleteness theorem, which was that so as long as we've got a theory we can axiomatize, that's a computably axiomatizable theory, and it extends Q, and it is one consistent, that is, it does not prove any false sigma 1 sentences. We had this result last week, that every one consistent computably axiomatizable theory, computably axiomatizable, extension of Q is incomplete. And in fact, the same argument, the same style of argument with some technical modifications would show that we can weaken the assumption of one consistency to consistency. So with a bit more work, which we did not do last week, but with a bit more work, one consistency can be weakened to consistency. So we have that every consistent so if we do that, we can remove the one consistent, and then we just get that every consistent computably axiomatizable extension of Q is incomplete. So as long as we can prove in our theory the properties of Q, the axioms of Q, and we can axiomatize it, we have a list of we can actually come up with a list of axioms. We can have an algorithm for producing the list of axioms, or equivalently an algorithm that tells us whether a sentence is an axiom. Then our theory is bound to be incomplete. That is, there is bound to be some sentence in it that neither that sentence nor its negation is provable. And that's essentially already what Gödel's first incompleteness theorem tells us. The shock of Gödel's first incompleteness theorem when it was first proved 90 years ago, when it was first announced to the world, was that people had hoped that the axioms for arithmetic would be sufficiently powerful that all truths of arithmetic could be proved from the axioms. People had hoped that would be the case, and Gödel's first incompleteness theorem showed that that was not the case. And even more than that, not only is the problem is not just to do with the axioms for piano arithmetic, but it is inherent in having a computable axiomatization. So as long as we can have this somehow, as long as we have an algorithm that tells us whether a sentence is an axiom, then, and as long as our theory is well, one consistent, then there is some sentence for which we can neither prove that sentence nor its negation. And because either the sentence or its negation, one of those must be true, there is some truth in the language of arithmetic, some truth about natural numbers that we cannot prove. So we already have an incompleteness theorem. Why do we need to go further? Well, in some sense we don't. But the incompleteness theorem we've got is also aesthetically unsatisfactory in a certain sense. At least for the purposes of this course, because it depended very heavily on computability theory. So in order to get the incompleteness theorem, the last week's incompleteness theorem, we needed to use results from computability theory, not very difficult results, but still we needed to use a particular result that we had a primitive recursive relation that allowed us by an existential quantification to define a set that was computably enumerable but not computable, or in other words, semi-decidable but not decidable. So last week's incompleteness theorem above depends crucially on computability theory. So what we're going to do today is, instead of following last week's approach, we're going to follow Gödel's original approach to proving incompleteness. The result we're going to get is essentially the same with a few more details in it. So it's still going to be, let's maybe put a box around last week's theorem. So it's still going to have this content, but with a few more specific details. But what it's going to, one advantage it's going to have is it's going to be self-contained. So it's not going to really rely so heavily on computability theory. Today we follow Gödel's original approach. So the advantages are that it's self-contained. We're not going to need to borrow a result from another area of mathematics, albeit computability theory is, of course, very closely related to logic. It's interesting. It's based on the notion of self-reference. A formula referring to itself. And it also leads to further developments. That are very important about the nature of incompleteness. And one of the most important of those we'll do next week. And that is Gödel's second incompleteness theorem. So that no theory can prove its own consistency. So this is an especially important further development, which in order to get this theorem, you need to go via Gödel's original approach to proving incompleteness for the first theorem. So Gödel's second incompleteness theorem. Okay, so there are plenty of reasons for looking at Gödel's original approach to his incompleteness theorems. So the basic idea we're going to start with is we want to have arithmetic formulas that express properties that state properties about arithmetic formulas. This is how we're going to get the self-reference. So we're going to have show that let's actually make an assumption first. So let's suppose that T is a computably axiomatized logical theory. Doesn't even need to be in the language of arithmetic. Well, let's make it in the language of arithmetic, just to not worry about too much generality, but in principle it doesn't need to be. Suppose T is some computably axiomatized theory. What we're going to show we show that properties of T such as formula A is provable in T, can be encoded as statements in arithmetic. So rather than saying formula A is provable in T, we're going to have a formula in arithmetic, a sentence in arithmetic, that expresses the property, the number that is the code, because we're going to code formulas as numbers, the number that is the code for formula A satisfies the number theoretic property that says I am the code of a formula that is provable in T. And we can express all that, we can express that number theoretic property as a, in fact, sigma 1 sentence in the language of arithmetic. So in order to do that, we need to code formulas and proofs as numbers, and properties as then arithmetic formulas. So we're going to, so first, we need to code formulas and proofs as numbers. And this job of this enterprise of encoding formulas and proofs as numbers is called Gödel numbering, because Gödel was the first person to employ it in his paper. Now, if we're programming, we're used to finding fancy representations for data structures that we want to code them up in different ways, as often using other constructions. We're used to the idea of, say, turning a string into a number or something like that. For example, if we want to have a hash table with strings as keys, and then we need to turn strings into numbers in order to get the hash keys out. So we're used to that in programming, but at the time that Gödel was doing this in 1931, nobody had done this sort of thing. And he wanted to encode formulas in the languages of arithmetic as single numbers. More generally, it's not just formulas. Formulas are built from terms. Formulas are built from terms and logical connectives and predicates. Terms are built from function symbols and variables and so on. So more generally, we want to encode all syntactic entities as numbers. Well, we're aiming in the end to get numbers representing formulas. And if we write down a formula, like for all x, there exists a y such that x equals the successor of y or something like that, that's a syntactically correct formula. And that's just a string of symbols for all, then x, then exists, then y, and so on. So essentially, to encode formulas, we want to be able to encode strings of symbols as numbers. So we're going to have a table for how we represent symbols as numbers. So we're going to have, so let's consider all the symbols we have in order to make formulas. Well, we have the equality predicate, the not symbol, the logical connectives, so that not is one, implies. All we need is a sufficient, we just need a sufficient collection of connectives to express any logical formula. We saw at the start of the course that we can get away with just not, implies, and for all. These were the particular connectives and quantifiers that made the Hilbert system, proof system, particularly easy. So we'll just have not, implies, and for all, and other connectives such as conjunction and existential quantification can be coded up. In order to write formulas properly, we're going to sometimes need brackets, so we'll put brackets in. And we've got the things from the signature. We've got 0, successor, the function symbols, successor, plus, and times. And then we also need some variables, and we need infinitely many variables potentially, since formulas might have an arbitrarily large number of variables. So I'm going to call my variables v0, v1, v2, and so on. And to each symbol, we give it a corresponding number. So let's not be tricky about how we do this. Let's simply number them starting from 1. It's useful to start from 1 for the way I'm going to do things later. So every number from 11 onwards is a code for a variable, and 1 to 10 are for the 10 other special symbols we have. And in general, if S is a symbol, I'm going to write #S for the code of the symbol S. So hash of equals is 1. So that's how we can encode. That's very easy, of course. That's how we encode individual symbols. Terms and formulas are strings of symbols. So for example, successor, well, the closed term, which is the numeral for 2, would be successor, open brackets, successor, open brackets, successor, open brackets, 0, close brackets, close brackets, close brackets. So that's a string of symbols. And we want a way of encoding strings as numbers. So a string of potentially n symbols, which could be the empty string, so n could be equal to 0. Sometimes people call these words. This is encoded by, so this is encoded by me write that up here. So to encode a string, I don't use the hash anymore. I use this. These are called the Gödel numbering symbols. And the formula for this, that's quite an easy formula, is to want to encode a sequence as a number in such a way that we can get the elements out of it. So we simply take 2 to the power of the number of the code of the first symbol times 3 to the power of the code for the second symbol times 5 to the power of the code for the, so this should be the second symbol, S2, the code for the third symbol, times, and the point is to use we're essentially using expansions as powers, as products of powers of primes. And so then we have Pn, the nth prime number, to the power of the code of the nth symbol. So where Pn is the nth prime number. So for example, some examples of these codings. For the symbol 0, we have the code of 0 is we just look it up on the table. The code of 0 is 7. For the string that contains, that is a string with one symbol in it, if we consider this as a string, then we use the string encoding, and then the code of the string that just contains 1, 0 is 2 to the power of 7. Notice this string is a term, a very simple closed term. And for the string, which is a formula, for example, the formula stating that 0 equals itself, so that's even a true formula, then the code of that formula is, well, it's a string with 3 symbols, so it's 2 to the power of the first symbol, which is 7, times then the second symbol, we take the second prime number, which is 3, so 3 to the power of the equality symbol is 1. So 2 to the power of 7 times 3 to the power of 1 times the third symbol is 0. So that's again a power of 7. And now it's the third prime to the power of 7. Okay, so we're encoding strings, symbols and strings as numbers. Some of you might be wondering, why do we need to encode sequences as numbers? Didn't we already do that using Gödel's beta lemma a couple of weeks ago? And indeed, we did encode sequences of finite sequences of numbers as individual numbers using Gödel's beta lemma. The reason for not using the beta lemma again is the beta lemma has the property that the number, if we're given a number, we know how to how to use the number as a sequence of length k, say for any k, in which case we can extract the first, second, third, all the way up to the kth elements of the sequence, as we did when we were reasoning the beta lemma. But still, the same number might be used to encode sequences of different lengths. So we can use the same number to encode a sequence of length 3 and the same number to encode a sequence of length 5 using the beta lemma. And that's not the case with this representation. So from this representation, if we're given a number and it is the encoding of a sequence, for it to be the encoding of a sequence, we because our codes from symbols are all greater than or equal to 1. Once we start with 2 to the power of something, we can't have any missing prime factors. So not all numbers are codes for sequences, but once we have a number which is a code for a sequence, we can get the length of the sequence from the code with this way of encoding. So that's why we use this way of encoding. So now, having encoded strings as numbers, we can consider various relations on numbers. So let's consider the following properties. Relations on numbers. So I'm going to define a property of numbers using term of n holds, and this is simply if and only if there exists a term t such that n is the code of t considered as a sequence of symbols. So basically, having coded sequences of symbols as natural numbers, we can then ask questions like, is a natural number a code for a sequence of symbols which is a legitimate sequence for a term? So in these examples here, this would be, this number's 2 to the, excuse me, this number 2 to the power of 7 is indeed the code of a sequence which is a term, because 0 is a term, whereas this number 2 to the power of 7 times 3 times 5 to the power of 7 is not a number encoding a term, because 0 equals 0 is not a term, but it is a formula. This is a number encoding a formula. So we can now, instead of asking whether a sequence of symbols is a term, we can ask, is a natural number the code of a sequence of symbols representing a term? And similarly, we can say formula n, and only if there exists a formula A such that n is the code of the sequence of symbols as a formula, and sentence. So a formula might have some free variables. We just the same as above, but sentence A. And in fact, by looking at the coding, it's easy to see that the coding of strings is 1-to-1, in the sense that if two strings have the same code, then they're the same string. So that means if n is the code for a term, it's the code for exactly one term. And similarly, if n is the code for a formula, it's the code for exactly one formula. And that implies the same thing for the sentences. And then we're going to consider a more fancy relation, which I'm going to call sub. And sub is going to have, well, let's use x, y, z, and w. It is still, I'm defining it as a relation on numbers, so x, y, z, and w here, standing for natural numbers. And what this is going to say is a bit more complicated. So it's that there exist a formula A such that x is the code of A. So x is a number encoding a formula. A term t such that y is the code of the term. A variable v sub I, the variables were numbered v0, v1, v2, and so on. Such that z, well, it's just a this is just a symbol, so we can just make z to be the code of the symbol vi. And a formula, well, sorry, there exist these such that W is the code for the formula A with T substituted for the variable VI. So the point is, this is the substitution operation that substitutes the term Y for the variable Z in the formula A. I mean, that doesn't make sense for numbers, but it makes sense when we interpret Y as a code, when we see that Y is the code for a term, Z is the code for a variable, A is the code for a formula, and this then performs the operation of substituting the term Z for, sorry, the term Y, the term coded by Y for the variable coded by Z in the formula A, and W is the result. Okay, so we can also code up important operations on formulas like substitution as a relation on numbers. And what I'm not going to prove, but it's not that hard, it's very tedious, are that all these relations are primitive recursive. So you covered what it means, what the definition of primitive recursive function and primitive recursive relation in the exercise class a couple of weeks ago. And you did enough exercises about primitive recursive functions to see how one can essentially do programming with primitive recursive functions, as long as you can essentially put bounds on searches. You can like You can do bounded quantification you can check that a property holds for all numbers less than a given bound, or for some number less than a given bound. And you can do things like you can sum all the numbers up to some finite bound, and these sort of operations. And using the programming facilities of primitive recursion, how do we implement these? Well, essentially what we've got is we've got a string of symbols coded by n. We want to see if it's a term or a formula or a sentence, and then we want to perform substitution operation. Essentially, this amounts to what in computer science is called parsing. So when one writes a program, it's like a long text file, that's a long sequence of symbols, and the compiler, before compiling it, needs to parse it to make sure it is a correct syntactic program. We need to just do the same thing here. It's like how we read a formula. We read the string of symbols and we check to see whether that string of symbols follows the rules for building a formula. Everything we do when we read a formula to check to see if we read a string of symbols to check to see if it's a formula, all that can be done in a primitive recursive way. And so all the above relations are primitive recursive. Okay, so it's 3 minutes past 9. If it's okay with you, I suggest we start again at 1:15. So we'll have a 12-minute break. So I'm going to pause the recording. Okay, so welcome back from the break. So before the break, what we studied was how to code sequences of logical symbols as numbers using this expansion as using products of powers of primes. There are many ways of doing it, but this is a convenient one. Then I just asserted that the relations, these predicates saying that a number n is a code for a term, a number n is a code for a formula, a number n is the code for a sentence, and the substitution relation W is the code for the formula obtained by substituting the term coded by Y for the variable coded by Z in the formula coded by X. So a more complicated relation. And all these relations are primitive recursive relations on numbers. We're taking that in trust, but you've done enough programming with primitive recursive functions in the exercise classes on the one hand to realize, I think, to hopefully be able to appreciate that this is sort of routine, but also on the other hand to probably know that you don't want to see the details for that. But if you want to think about it yourselves, then you're welcome to do so. Anyway, so we have primitive recursive relations expressing these primitive recursive relations on numbers expressing these properties, being a sentence, a formula, a term, and substituting a term for a variable in a formula. Now we want to use these, and to do so, let's remind ourselves of if you've got primitive recursive relations, we can represent them using logical formulas. So every primitive recursive relation is sigma 1 representable. So a primitive recursive relation, as you know from the exercise classes, is a relation whose characteristic function, that's a function from k-tuples of natural numbers that returns 1 if the k-tuple belongs to the relation and 0 if it doesn't. A primitive recursive relation is a relation whose characteristic function is a primitive recursive function. By the work we did on representing the exponentiation function 2 weeks ago, we saw how to represent that as a sigma 1, how that function was sigma 1 representable. I told you last week, I think that generalizes to arbitrary primitive recursive functions are sigma 1 representable, and from that it's an easy consequence that primitive recursive relations are sigma 1 representable. So essentially we've done this material. Is basically the same proof as the sigma 1 representation, sigma 1 representation of the exponentiation function, with adapted to general primitive recursive functions and then transferred to relations. So the main interesting details were in the proof. So we haven't had it explicitly in this form, but though we have had it for primitive recursive functions last week. But even though we haven't had it in this form, we know this. So I think that's a better way of saying. And as I say, the main difficulty in the proof is is essentially already present in proving that the exponentiation function is sigma 1 representable. We could have done this proof in full generality, but it's the same idea, is just a lot more tedious because one's dealing with the general formulation of primitive recursive functions and then relations. So the interesting work has been done explicitly, and the tedious work we're not doing. So we know that. So not only do we have primitive recursive relations, by the general representability result, we have sigma 1 formulas that express these relations. Now, actually, what we want is that not only are there sigma 1 formulas that express the relations, but so expressing the sigma 1 formulas representing the relations with our definition of representability, all that tells us is that the sigma 1 formula for a tuple of natural numbers n1 to nk is true in the natural numbers if and only if the x n1 to nk are in the relation R. So the truth of the sigma 1 formula in the natural numbers is the same thing as the tuple of natural numbers being in the relation. Now that's not quite good enough for what we're going to need to do, because we want to reason in our axiomatic theories. If we go back to the axiomatic theories, and again we're only going to assume that our axiomatic theory extends Q. So a sigma 1 formula that happens to represent the relation, if we look at the truth of the formula in the natural numbers, is not necessarily going to be very helpful, because we want to actually prove properties about the represented function using Q or some extension of Q. So we now need to take a little technical moment that's not going to take very long and get a stronger version of representability that tells us that Q can prove sufficiently many properties of the represented relation. So let's write that down. So we need a stronger representability result. But fortunately, we can derive the result we need from the result we already have, which is the one in the red box. So this is going to be a lemma. Let's see if I've got enough space for it. Yes. And this, it says, for certain kinds of relations, we can represent it by we can represent certain nice relations by a sigma 1 formula in we can represent certain kinds of relations by a sigma 1 formula in a strong way that Q can prove more properties of it than are guaranteed just by representability. So this is called strong Q representability. And as you'll know from the exercise classes last week, there's a lot that the theory Q cannot prove. So it's quite intuitive, given that one needs to work rather hard to code things. One needs to work a little bit to make sure that one states properties in a way that Q can prove them. If one needs Q to prove something, you need to be you need to be careful to make sure that you really can prove it just from those few axioms in Q. So strong Q representability is going to work in the following circumstances. So suppose R is a primitive recursive relation. And sorry, I need to say how many arguments it's got. So we've got k plus 1 arguments. And the point is, what we want of it is that it's the graph of a partial function from the x's to the y. So a partial function with k arguments. So it's a primitive recursive relation such that, so we want it to be a partial function, a graph of a partial function. So for all n tuples of natural numbers, sorry, k tuples of natural numbers for the x variables, it's a partial function. So we want to say there is at most one y, at most one m for y, for which such that R holds for n1 through to nk and m. Okay, so it's a partial function in the first k arguments. So in these circumstances, so the point of this lemma is that if you've got a partial function whose graph is primitive recursive, is a primitive recursive relation, then its graph is sigma 1 representable in the following strong sense. So there exists a sigma 1 formula such that two properties hold. So firstly, let's call it A sub r. So if Q proves that A sub r holds for n1 to nk to m, then n1 through to nk and m are in the R relation. So this will hold if AR is any sigma 1 formula that that represents the relation R, because if Q proves it, well, the axioms of Q are all true, then it's true in the natural numbers, and then if A is a formula that represents R, this implication holds. But the point is we want a stronger converse implication than we would normally have, which is that if for the converse implication, we have for all n1 through to nk, so notice this implication is not, so here we've got Q proves this sentence, and if Q proves this sentence, then the numbers are in the relation. But for the other direction, for all n1 to nk, what we're going to require is that Q for all n1 to nk, sorry, I wanted to say this. So the other implication, so it's for all n1 through to nk and m, it's that if we have a tuple that in the relation R, then not only does Q prove that it holds, does Q prove that AR holds, which would follow from sigma 1 representability, because if we have sigma 1 representability, then the AR relation is true, and then by sigma 1 completeness of Q, Q proves it. But we want Q to do something stronger, which is Q proves that for all y, if that AR holds for A1, N1 through to NK of Y, if and only if Y equals M. So not only does Q prove that AR holds for N1 through to NK and M, but Q is strong enough to prove that M is the only value for which that relation holds. Okay, so it's a bit more than what follows just from assuming that AR is a formula. AR is the sigma 1 formula that shows that the relation R is sigma 1 representable. I should say that if I want to be really careful here, maybe these are sentences, So here I'm really substituting the numerals in, because I'm substituting the terms for the numbers into the formula AR. So let's put all the numerals in. Okay, so we want to prove this. So because R is primitive recursive, it is sigma 1 representable by the result I put in the box. It's primitive recursive. So we just need to show it's sigma 1 representable in a nice way that has this more powerful property that Q, even though it has no induction, can prove that M is the unique value that's in the relation. For any fixed N1 to Nk, it proves that M is the unique value. So because R is primitive recursive, there is a sigma 1 formula B that represents it. So B that represents R. And this formula B will satisfy this implication, because if Q proves that B holds for a K plus 1 tuple of numbers, well then, because the axioms of Q are true, then B really holds for that K tuple of numbers, and therefore by the sigma 1 representability, R holds, though that K plus 1 tuple is in the relation. But this implication might not hold, because all we'll get is that if we have a K plus 1 tuple in the relation, then Q proves by sigma 1 completeness, Q proves that B holds of that K tuple N1 to Nk with M. But there's no reason for Q to be able to prove that that M is the unique value for which the unique value that's in the relation with respect to N1 to Nk. However, if R is a primitive recursive relation, then its negation is also primitive recursive. You just invert the characteristic function. So represented by so there is another sigma 1 formula, C, that represents not R. So the idea now is to use the formula so instead of using B, which sigma 1 represents R, the idea is to use the formula saying that B holds and not only does B hold for a tuple x1 through to xk and y, but for all z less than y, strictly less than y, B does not hold. So y is not only in the relation R, but it is the least number in the relation. So we're going to explicitly say in our relation that y is always the least number in the relation. That forces there to only be one value of y that will fulfill the condition. The only problem is we can't use this formula directly because it is not sigma 1. This is not explicitly sigma 1. So we need to do something a little bit different. Well, essentially, we're going to find a sigma 1 formula that essentially expresses the same property as this. So suppose B xky, this is a sigma 1 formula. So suppose this is of the form, there exists z1 through to zm, say, b prime x1, well, let's just say b prime. So this we'll have three variables, x1 through to xk, y, and z1 through to zm. And C is exists w1, wm, c prime, where importantly, these two formulas are delta 0. So they only have bounded quantifications. Then we define, so then we're going to essentially move the quantifiers around to encode this formula as a formula, as an explicit sigma 1 formula. So we then define AR, the sigma 1 formula we want to be. So we want to move all existential quantifications on the outside, but here there's a bounded quantifier that we need to negotiate as well. So I'm just going to write down the right thing and you can think about it. So essentially we're going to, we pull these existential quantifiers from B on the outside. So we have exists Z1 through to Zm. And instead of pulling the W's to the outside, we're going to assume there exists a bound for the W's. So we'll say there exists a V such that then B prime, that's what's inside the existential quantifiers for B. And now we want to have some bounded quantifiers. So we have for all Z less than y. And we're going to replace all these w's with bounded quantifiers bounded by v. So there exists a w1 less than equal to v dot dot dot. There exists a wm less than equal to v c prime. And it's easy to convince yourselves. I'll let you think about this. You can look at the notes and think about it. It's easy to convince yourselves that this formula is equivalent to this formula. Essentially, because if for all z less than some y, there exists w1 through to wm, then because there are only finitely many z's, there must be some uniform bound v that we can find for w1 to wm. That's the essential argument. You can think about it for yourselves. So one can convince oneself that this formula is equivalent to this one, and that then that it does the right job. Actually, the equivalence between this black formula here and the blue formula here, I don't think that can be proven in Q. It doesn't matter, because then it can be proven in Q that this formula does the right job in the sense that it fulfills these bullet points. And that uses the last week's lemma. So then, last week's lemma is about bounded quantifiers. If you're bounding less than or equal to a numeral, then you can expand it out as a disjunction of all the cases given by the numeral. So this works using last week's lemmas about Q. Last week's lemma about bounded quantifiers in Q. About bounded quantification in Q. Okay, I think that's enough details for that. What we've got with this is we have the notion of strong Q representability. It's rather technical, as you can see, but this is going to be crucial now for the next lemma that we're going to prove, which is now the cornerstone of Gödel's incompleteness theorem. And this lemma is the lemma that encodes self-reference. And we'll see maybe just before going to that, just one thing to say, that so this notion of strong representability that we've got here, it crucially relies on the relation being a partial function. So the y, if it exists, is uniquely determined by x1 through to xk, because the whole notion of strong representability involves saying that it only strengthens representability by saying that Q can prove that the Y is unique. When such a value M exists, Q can prove that it's the unique one. So just to say, the substitution relation, which it's going to be very important that this is a partial functional relation. Then if we're given numbers for x, y, and z, well, we know, I've already said that a number is a code for a unique formula, at most one formula. If it encodes a formula, it encodes a unique formula. Similarly, a number is a code for a unique term if it encodes a term. Similarly, a number is a code for a unique variable if it encodes a variable. So if we have an x, y, and z for which there exists some w in the relation, the formula a, the formula t, and the variable vi are uniquely determined, in which case the substitution is determined itself by a substitution algorithm. We define the substitution algorithm so that the substitution is uniquely determined. Okay, so that is a partial functional relation. We're going to need that, I think, after the break. So the next lemma is a very important lemma, and it captures the idea of self-reference. Which was yet another of the major contributions of this lemma is yet another of the major contributions in Gödel's paper on his incompleteness theorems. So this is called Gödel's diagonal lemma. So this says for any formula with one free variable. So I'm going to call the free variable v0. Of course, it doesn't matter what the free variable is. Doesn't matter what name we give to the free variable. So I'm saying this to emphasize that we're now thinking of formulas written in the same language that we are encoding. So the language that we are encoding is here. So we're thinking of formulas written in the parsimonious language, which just for convenience is just using negation, implies, and for all. And these symbols and the variables are v0, v1, and v2. So I'm just emphasizing that we were actually writing our, excuse me, we're writing our formula using the symbols that we're encoding to encode formulas. So there is a sentence B such that in Q can prove that B is equivalent to, so B if and only if, so this is A holds with the code for B substituted for the variable B0. So this is, Q can prove this if and only if. So I know if and only if is not in our language. So really, I mean the conjunction of B implies A of B and A of B implies B. The conjunction's not in our language, so I really mean the formula that is obtained from that conjunction by encoding the conjunction using negation and implication. But obviously, it would not make things more readable to write that formula out directly. So we know that we can do such manipulations and put it in the parsimonious language that only has negation, implication, and for all, but we're not going to actually do that to formulas that we want to ourselves read. So here, what do I mean? Well, A is a formula that has at most one free variable v0. Here I'm substituting the code for the sentence B for that variable v0. So if I was being really fussy, I need to substitute a term, not a natural number. Natural numbers are not themselves formulas. So really, I should be substituting the numeral for the code for B here. But, well, actually, let me put that also in blue. So blue is kind of stuff that one can ignore. So here we have the numeral for the code for B, but again, it will get very tedious to always write these numerals on. And if I say a formula A with a number substituted for a variable, then it's clear that I mean the numeral substituted for the variable. So this is a very important lemma. Its proof is rather technical, and I think its proof should be left until after the break. But before going to the break, let's paraphrase what this lemma says, because it states an interesting property. So A is just some property about numbers. You know, but we're in number theory, we're in the language of number theory, the language of arithmetic. And so any formula in a free variable is expressing a property of numbers. It could be the property that a number is prime. So paraphrasing, that means stating it kind of informally, in other words. A little bit summarizing. For any property of numbers A, there exists a sentence B that asserts the property. So B is equivalent to A holds for the code of B. So it asserts the property A holds for my code. Or if you really want to paraphrase, or perhaps A holds for me, if you like. Or let's say I satisfy A, or my code satisfies A. Let's say I satisfy. Well, maybe I is too much, but my code satisfies A. So I'm a sentence, and I say my own, I'm a sentence B. There is a sentence B that says, essentially, my own code satisfies A, because B is equivalent to A holding for its own code. Very curious little lemma. And what we're going to do after the break is we'll prove the lemma first. We'll get the hard work out of the way. It's rather technical. And then we shall see that Gödel's second incompleteness theorem, the very beautiful incompleteness theorem, then follows from it with a bit more work, but not too much. Okay, so well, we had a short break the first time, and it's close enough to 10 that we'll have the full 15 minutes break and start at 10:15. So I'll pause the recording. Okay, so welcome back. So we ended the last part with Gödel's diagonal lemma, which, loosely paraphrased, says that for any property A expressed by a first order formula, so any property of numbers A, we can find a sentence B that because of this equivalence, B is stating that its own code satisfies A. I just simplified this. There didn't seem to be any point writing the same thing twice. So B is a sentence saying my own code satisfies the property A. That's a bit strange. And not only does that equivalence hold, it's not only a true equivalence as a property of natural numbers, this can even be proved in the very weak theory Q, that B is asserting this property. So we're going to prove this. It's a very mysterious proof. So first we're going to consider a slightly modified substitution relation. So we've got a substitution relation sub x, y, z, w, saying that if we substitute a term for a variable in a formula, then we get w back. We're going to simplify that to just the one we want. So we're given the formula A with a free variable v0, potentially with a free variable. So let's consider the relation that's only a three-way relation. I'll call it sub-num. X, Y, Z. And this expresses the property that the X is the code of some formula D. Y is n, any number n. Well, let's actually put it like this. M, N, L. So this relation holds for numbers M, N, and L. If and only if M is the code for some formula D, and L is the code for D with the numeral for N substituted for V0. So we're simply performing a substitution operation. We only need 3 arguments this time because the variable has been chosen to be V0. So we don't need a code for the variable. And moreover, the term we're substituting, the N, sorry, let's write that a bit neatly so it's clear that's an L. The term we're substituting, the N, well, sorry, the argument for which we're substituting, we're not passing a code for a term, we're passing a number, and we substitute the numeral for that number. So this is primitive recursive. it's just a small modification of the original substitution relation. Hence, strongly Q representable. By a sigma 1 formula. So we should check that it's a partial function from m and n to L, but that is the case because it's defined for all n and for appropriate m that are codes of a formula, and L is again simply defined by a functional operation, which is substitute the numeral n for the variable v0. Okay. I'm going to write, so rather than writing a sub num in the strong representability lemma, we were using some complicated a sub r. Rather than writing that, I'm just going to use sub num itself for this formula, just for readability. So for readability, we write sub num xyz for this sigma 1 formula. So now I'm going to define a formula. So consider the formula C, which is going to have one free variable v0. And this is so C is going to be the formula. There exists a y. Well, let's make it clearer in our vocabulary. So there exists a v1 such that sub num v0. Let's make these subscripts here clear so they can be read. v0, v1, and a of v1, replacing the v0 in a with v1. So this is in our original vocabulary. Okay, I'm using conjunction and existential quantification, but again, one needs to translate this to not for all not and replace the conjunction with negations and implications, but I want to keep things readable. So for any formula D, we have that the formula C, if we substitute in C the code for D, so then we're substituting the code for D for V0 here. We get there exists a V1 sub num the code for D. We're substituting D for V0, the code for D, V1 and a V1. So loosely speaking, what this is saying is there exists some number V1 that is the code for the formula D with its own code substituted for the variable V0 in D, if it occurs in D. And for that substituted formula D with its own code substituted for V0 in D, for that substituted formula, the code of that substituted formula, A holds for it. And we have that Q proves that C of D, which is this, holds if and only if, well, so C of D says there exists a V1 such that that is the code for D substituted for the numeral for the code for D substituted for the variable V0 in D. Now, because D is a formula, we can indeed take the numeral for the code of D and substitute it for the variable V0. So there is indeed a number V1 that for any formula D, there is a number V1 that is the code for the formula D with the code for D substituted for V0. And that is the code for so maybe I'll say it here. So, and we have that in the relation subnum, so there can be at most one thing in this relation, but we know what it is. There is a number in this relation. It is the code for D with the code for D substituted with the numeral for the code for D substituted for V0. So because this is a primitive recursive relation, and this is strongly representing this primitive recursive relation, that there is at most one thing in this code, Q can prove that if there exists something in this, it needs to be the strong notion of strong representability gave us exactly that it needs to be the actual number that that satisfies the relation. So Q proves that C of D holds if and only if A holds, so there's exactly one value for V1, and it is this code for D with its own code substituted for V0. And so C of D holds if and only if A holds for that unique number that can be V1. So A holds for D with D with the numeral for D substituted for V0. So by instantiating in the case so in particular, if we consider the case that D is, so this was for any formula D. If we consider the case that D is itself C, that D, if we consider the case that D is the formula C, then Q proves that C with its own code substituted for V0 holds if and only if A holds of C with the numeral for the code of C substituted for V0. But this is here what we're doing is this notation means substitute the numeral for the code of C for V0 in C. So this is exactly A of the formula C with this notation just meant the numeral for the code of C substituted for V0 in C. So we're done because this formula here, C with the numeral for the code of C substituted for V0 satisfies the right equivalence. So we are done by defining B to be the sentence C with the numeral for its own code satisfied substituted for V0. Okay, rather mysterious proof. You can think about it in your own time. The only thing here I want to add is this equivalence here. This was by strong Q representability. We were going from there exists, Q knows that if there exists some value that's in this subnum relation, then it has to be the exact value because it can, Q can, strong representability gives us that Q proves that there is a unique number that's in this relation. So this if and only if is by strong Q representability. Okay. So we've proved the diagonalization lemma, and we can now go to Gödel's second incompleteness theorem. So the diagonalization lemma says that we can find a sentence B that says A holds of myself. And Gödel's idea use the diagonalization lemma, the diagonal lemma, use the diagonal lemma to find a sentence that says I am not provable. And then if it's true, it's not provable. And if it's false, well, then it will be provable, but then we can prove something false. And that wouldn't be good. Okay, so we simply need to apply the diagonal lemma. Here we are, to a formula that says V0 is the code of a provable sentence. But how do we express that property A? We need to have some relations in the, we need to have formulas in the language of arithmetic that express whether or not a number is a code of a provable sentence. So to do that, we need to extend Gödel numbering. So we need to extend Gödel numbering. We've so far Gödel numbered sequences of symbols to give us terms and formulas, but we need to extend Gödel numbering now to proofs. But this is easy if we use a Hilbert system. So a proof in a Hilbert system, in the Hilbert proof system, the Gentzen system was a bit more complicated. Is just a sequence of formulas following some rules. So every formula needs to either be an axiom or the conclusion of, so including our axioms for whichever theory we're using, like piano arithmetic or something, or the conclusion, or it needs to follow by one of the inference rules from some of the previous formulas we've established and we've already put in the proof. But anyway, it's just a sequence of formulas subject to some rules. And is a proof an acceptable proof? So we simply code proofs as sequences of codes for formulas. So we code a proof as a sequence, as a code of a sequence of codes of formulas. So there's nothing really difficult. A code of a sequence of codes of formulas. And if we do this, the relation proof, all right, proof P n, which holds if and only if P is a code. Well, let's work on n first. So n is the code of a formula A. Oh, sorry, I want that. I'm just going to write it more symbolically. So n is the code of a formula A, for some formula A, and P is a proof of it. P is the code of a proof of A. Okay, so we can say, does a number code a proof of a formula encoded via another number? So this, unsurprisingly, is primitive recursive. Well, there is a condition here. So I'm saying a proof, but from what axioms? So let T be some axioms for a theory. So from the axioms of T. So it's a proof of A from the axioms of T. And this is primitive recursive if T is computably axiomatizable. Because if it's computably axiomatizable, it's in fact primitively recursively axiomatizable. And we'll just accept that. It's not a deep result. So this is primitive recursive if T, and in fact only if, is computably axiomatizable. And really the actual relation we get depends on the axiomatization. So it's really, given a computable axiomatization, we have a primitive recursive relation. Because depending on the axiomatization, the notion of being a proof will change. So this is now, again, partial functional in this direction, that a proof determines a unique conclusion. Don't think we're going to need that, but again, we so proof T is strongly Q represented by a sigma 1 formula, which I'm simply going to write as this formula as proof T xy. Okay, so the proof relation, PRF relation, says X is the code for a proof of the formula coded by Y. And we define the provability predicate, proof T of Y, is simply defined to be there exists an X such that X is the code for a proof of Y. So again, this is a sigma 1 formula. So NB proof T, well, sorry, because being a code for a proof of was a sigma 1 formula because this was representing a primitive recursive relation, and now we've just existentially quantified over a sigma 1 formula, so we stay sigma 1. So what I want to say, proof T of Y is sigma 1. And now we can define the sentence we want to, which says, I am not provable. The Gödel sentence. For computably axiomatized T. So I'm saying computably axiomatized because, as I said above, I was being a little bit careless. Somehow it depends on our computable axiomatization. So given a computable axiomatization, we can come up with a coding of proofs, and then we have the proof relation and the proof T relation. So it actually depends on the axiomatization we have. But still, in theorems, I'll say if the theorem's computably axiomatizable, and we just assume we're given some axiomatization. So the Gödel sentence is defined to be, it's this. So we simply use the diagonalization lemma the diagonal lemma to define, or to find a GT, a sentence GT, to find a sentence GT satisfying, so the Gödel sentence for the theory T, that's why it's called GT. So it satisfies that in Q proves that GT, whoops, asserts I am not provable. So my code is not in the provability relation for the theory T. Does not satisfy the provability of codes for the theory T. In other words, I am not provable. So let's call this star. Okay, so the diagonalization lemma said for any property of numbers, we could find a sentence that says my code satisfies that property. If we have the property that for in the provability relation saying a number satisfies me if I am the code for a provable formula. So the provable relation is saying there exists, I have some proof. The formula coded by me has some proof. And so here GT is saying the formula coded by me has no proof. In other words, I am not provable. And now we can state Gödel's first incompleteness theorem. Axiomatized primitive computably axiomatized consistent extension of Q. So we're going to get an incompleteness theorem that says that as long as you've got a consistent theory, then T cannot prove its own Gödel sentence. If T is one consistent, so if all provable sigma 1 sentences are true, then it also can't prove the negation of its, Gödel sentence. And thirdly, the Gödel sentence is true. So even if T can prove the negation of its Gödel sentence in a consistent but not one consistent theory, then in that case, T is proving a false sentence, which is something we don't like. So compared with last week, we found an explicit sentence, GT, which is true and not provable. And as long as our theory is one consistent, the negation is also not provable, giving us incompleteness. And the proof is now very straightforward. So for 1, we want to show that GT is not provable. So suppose GT is provable for contradiction, then because GT says I am not provable, so by star, well, this is provable in Q, so it's provable in T because T is an extension of Q. This is where we need that T is an extension of Q. Anyway, Q has such few simple axioms. We certainly want our theory of arithmetic to be an extension of Q. So by star, this means T proves, so GT is equivalent to not proven T, GT. But also because T proves GT, then, well, GT is provable, so but GT is provable in T. So by the way, we defined the provability relation. So in the natural numbers, it's the case that the provability relation says it holds of the code for a formula if and only if the code is provable. That's how we define the provability relation. And so, and since Q is sigma 1 complete, sigma 1 completeness, this is a sigma 1 sentence of Q and hence of T because T extends Q. T also proves that the code of GT is in the provability relation, but this contradicts consistency because we've got not that T proves a sentence and its negation, contradicting consistency. Okay, that's property 1. Property 2, we want, so suppose T is 1 consistent. And we want to prove that T does not prove the negation of the theory T does not prove the negation of the Gödel sentence. And suppose T does not prove the negation of the Gödel sentence. So then by star, sorry, we want to prove that it doesn't prove the negation of the Gödel sentence. So suppose for contradiction that T does prove the negation of the Gödel sentence. So by star, then T proves the negation of GT is not provable. In other words, T proves that GT is provable. But this is a sigma 1 sentence. So by 1 consistency, every sigma 1 sentence is true. And it's true in the natural numbers that the provability relation holds for GT, but this just says that GT is provable. And again, this contradicts now consistency, which follows from, well, which was anyway assumed, but also follows from one consistency. So again, contradicting consistency. And thirdly, well, we want to show that that GT is true in the natural numbers. So we have, again, by the definition of the provability relation, we have that, I've been using this already, for any sentence A, the provability relation is true in the natural numbers if and only if T proves A. So by 1, we've said that T does not prove the Gödel sentence. So by 1, so by 1, T does not prove the Gödel sentence. So it's not true in the natural numbers that the statement saying that the code for GT is in the provability relation. So then by star, well, this is the negation. By star, this is the negation of GT. So the negation of GT is false. So in other words, GT is true. And we're done. Right on time. So there we are. With the diagonalization lemma, that was the main job. And the coding, well, the two jobs were the diagonalization lemma and being able to code properties of formulas like substitution, and crucially then the provability relation, the provability predicate for a computably axiomatized theory. And there we have Gödel's first incompleteness theorem, which has explicitly found, using the diagonalization theorem, a true sentence that is not provable, and also, as long as we are one consistent, its negation is also not provable. So that's the end of today's lecture, and I shall stop the recording.